All right, let's look at the law of cosines. All right, so if you have an arbitrary triangle A, B, C, then the following equality is true. A squared is equal to B squared plus C squared minus 2BC cosine of A. Right, and symmetric equality holds for the other angles too. Right, so let's just to pick on the first one. Right. Right, proof for the other one are just symmetric, so we don't have to do those. All right, let's focus on that one. All right, so again, there are three cases, just like the proof for law of cosines. So we're going to consider those three cases. And the case 3 is actually given in the book, so I'm not going to do that. And the case 2 is very similar to case 3, so I'm not going to do that. Let's just do case 1. Right, so A and B are acute angles. Right, so we have acute angles. Right, so let's start with so we have to start with the left hand side. So let's start with A squared. Right, so using Pythagorean theorem, h squared can be written as h squared plus c2 squared. So it's h squared plus c2 squared. Right? Right, so since I want to get the b squared somehow, so we can get that by using another Pythagorean theorem. H squared is b squared minus c1 squared. So we can write it as h squared is b squared minus c1 squared. Right? Then you have a plus c2 squared. Right? And the c2 squared, I want to get some c involved. So what we're going to do is I'm going to actually replace this guy, c2 squared. C2 squared is the same thing as c minus c1 squared. So plug that in. So we have a b squared minus c1 squared. Right? I'm going to just multiply this guy out. So it's going to be a c squared minus 2cc1 plus c1 squared. Right? And luckily, we can cancel c1 squared with a negative sign and the c1 squared there. All right, so looks like we already have what we want. We have b squared there, and we want to have c squared there. So somehow we have to get the cosine of a involved. Right? Cosine of a is equal to, right, cosine of a here, so it's cosine, so it's going to be adjacent, so c1 over hypotenuse, so b, c1 over b, which gives you multiplied by b. So b cosine of a is same thing as c1, right? So we can plug this guy in here, right? So what you get is b squared plus c squared minus 2c. c1 is b cosine of a, right? Which is exactly what we wanted to get, right? So this verifies the law of cosines. Right, so other cases can be done similarly, and the case 3 is, I believe, given in the book. So, and the case 2 is very similar to case 3. All right, so law of cosine is kind of like, you can think of this as the generalization of Pythagorean theorem. For example, let's pick on easy one to pick would be this guy, right? So this is law of cosine there. What if if C happens to be 90 degrees, so you have a right triangle. So then you know that the cosine of C is going to be 0, right? So which means that this law of cosine becomes c squared is equal to a squared plus b squared, and this last term is going to be 0 because cosine of c is equal to 0. This is just a Pythagorean theorem. So Pythagorean theorem is basically a special case of law of cosines, right? That's that. I hope that this was clear.